This evening I'd like to talk about how we moved from science to startups with computer vision, TensorFlow, and people. So I've just finished my PhD in computer vision and soft biometrics from the University of Southampton. Recently published a paper called Superfine Attributes with crowd prototyping in TPAMing. I'd like to talk about that a little bit. More recently, Jamie is here in the audience. Jonathan and myself co-founded Aura Vision, which is a video AI platform to help retailers measure and improve every shopping experience. We're going to talk a little bit about the transition from academia to business, some of the challenges involved, what's the same and what's different. So it all starts in 2013. So this is the Boston Marathon bombing. It was a horrific event. It was pretty devastating. The crowds there were very dense. It had made a lot of damage. But there was also a lot of security. There were a lot of cameras pointed at the area, but it still took surveillance operatives over 3 days to identify the suspects. So as soon as the bomb went off, a manhunt started. Like, the internet was searching for these guys, police teams, surveillance teams all searching for them, but it still took 3 days, even though there were cameras covering the event everywhere. And the reason for that is because faces are really hard to spot in crowds. You can't see any faces down here. The two really clear CCTV shots we get of the suspects down here don't include their faces. So while we managed to capture them at the top there, a facial recognition system, which would have been state-of-the-art for recognizing them at the time, wouldn't have been able to work with these types of images. This is a really big problem because surveillance teams and police departments all over the world spend hundreds of thousands of hours every year on just crawling through video footage, looking for their suspects, seeing where criminals went. And actually this problem's set to get worse because internet video surveillance is looking to grow 7 times in the next 3 years. This is a really important problem to solve. So we need to find a way of finding people without being able to see their faces. So a lot of my PhD was invested in soft biometrics. So soft biometrics are unlike hard biometrics. So the kind of biometrics you think of will be hard biometrics like facial recognition, iris scanning, DNA detection, but soft biometrics are almost the opposite now. So hard biometrics are great because they're really discriminative. You can have one, you can uniquely identify someone most of the time. They're really difficult to capture. You can't capture them in a CCTV image. But soft biometrics are the opposite. You can see a lot of soft biometrics in this super grainy, blurry image of this guy here. We can tell that he's a guy. We can roughly tell his skin color, his hair color, he's got short hair. You can make a vague estimation on his age. And actually, when you put all of the pieces of information together, you get a pretty good, unique descriptor for that person. And what makes it different is that they're visible at a distance, and they're also often invariant to angle and pose, so they'll stay the same even if they're changing angle in the camera. So it should be easy, right? We should just be able to label a few 100,000 images, run a crowdsourcing task, labeling like gender and age, and then we'll train a model, and that model will estimate these demographics, and then we can just use that as a system to identify people. So I'm just going to try and simulate the first bit of that with you guys in the crowd right now. So we're going to label the gender of 3 images. So who thinks, just raise your hands if you think this is a female image. So almost all the room thinks that's female. It's a bit low quality, but we're pretty certain that. It seems to be holding up so far. How about this image? Who thinks this is a person that's female? Raise your hand if you think this is a female. Or we've got like a few hands. How about male? Who thinks this is a male? Okay, so like quite a bit of the room thinks it's male. I'd say like 70 to 10%, maybe like 20% of people didn't answer. So the binary categories are kind of slightly breaking down, but maybe they hold up. So this third image, this is a pretty typical image to get out of the CCTV system. Who thinks they'd be certain to label this as female? Oh, a few people. What about male? Who thinks this is male? Okay, about the same number of people, but a massive amount of people didn't answer that. And this is actually the factual case that these are the types of images that surveillance ops and machine learning algorithms have to label all the time, because this is what you see in CCTV. So I think that we need a better way of labeling these images. So how can we precisely label any image that comes out of the CCTV system, no matter what quality or where it's from? So in this paper, we introduced a concept called superfine attributes. So categorical and binary attributes are what are de facto for re-ID datasets and pedestrian datasets, where they're looking to build models that learn age and gender. The problem with these types of labels is they don't account for ambiguity or uncertainty. So this image here is very blurry. Labeling that as male or female is actually completely irrelevant. It doesn't make sense. And for this image, it might make sense, but you're going to get inconsistent responses. And the upshot of that is that the classifiers poorly generalize. They're learning anti-patterns, they're learning things that they shouldn't be learning, which makes them worse overall. So what we want to do is move from that space to a superfine attribute space. So it looks kind of complicated, but it's actually really simple. It's just projecting these images as multi-dimensional coordinates in a continuous space, rather than having them as like a fixed binary or categorical label. So for example, this female image, she's very female and very clear. So she's on the end of the gender spectrum, she's a female, and on the uncertainty axis, she would be a clear image. Whereas this one is blurry, we can't really tell what the gender is, so it gets about 50-50 gender, but it's very obviously an obscured image, so it gets shifted to that end of the axis. And this is really important because it allows you to describe multiple concepts within that image that would be described under gender. And it's a more objective way of comparing the similarities and differences to different types of images. So it's great, but we need to work out what this space is before we can do anything. So the way we do this is through crowd prototyping. So what we do is we crowdsource pairwise similarities between two images at a time. This is really inefficient because we need to do n choose 2 comparisons. So we only pick a small subset of 95 subjects in this paper to do this with, and we label every single pair of those subjects. So for example, we'll say, okay, the person on the left and the person on the right, how similar or different is their gender? So we'll get a distance between them. So from that, we actually build up a distance matrix, which is just a square matrix of n by n subject dimensions. It's symmetric, so it's just a triangular symmetric matrix. And then what we want to do from that is form an embedding from it. So we actually embed it with a technique called metric MDMS. And what the embedding is doing is taking it from a super high dimensional space down to a much lower dimensional space, in this case just 2 dimensions. And that's removing a lot of the noise in the annotations, but it's also finding the salient axes. So it's finding that gender axis, it's finding that obscurity axis, and then we can project our images into this much clearer, cleaner space. The way it does it is actually really simple. It's just measuring the error on Euclidean distance. So if you're saying that two images are very different, we want them to be very different in the embedded space as well. So once we've found this space, we've got our little images in there, we just apply clustering to that. So it's very basic. You can use any algorithm. In this case, we use annumerosive hierarchical clustering. And we just clustered it into 5 different regions. So this region over here, this purple region, relates to these types of images. So we can see these are all very clearly female images. And as you move away from that region, they will get less female and go towards other concepts. So that's the hard work done. We found the space, we've worked out what this superfine space should be. Now the easy bit is labeling new images into that space. So that space is created only from 95, but we've got 20,000 that we need to label more efficiently. So this exercise is easy, it's another crowdsourcing task. You just match the new image to whichever prototype it's most related to. So for example, she would be matched to the female prototype because she's visually most similar. It's a more objective way for humans to actually label new images. So this is what it looks like once you've labelled 20,000 images with superfine age attributes. So we use this PETA dataset. At the time, it was one of the largest ReID datasets. It was built from 10 different ReID datasets captured across the world. So it's very diverse. There's a lot of intra-class variants. And it came with 108 binary attributes, so the images were labelled with these binary attributes that we could benchmark our solution to. So the age is really interesting because we get very young people at the top left, and then we get this gradient of age through the space. So they get older and older and older through to quite very old over here. That's exactly what we'd expect because very young and very old are visually the most distinct classes. So you can see that there's going to be a large distance between them. So it's exactly what we expect. And as they become more obscure, they kind of cluster into the middle here because you can't actually, when they become extremely blurry, you can't tell anything about the age, so you haven't got any discriminative age features coming out of that. So the proof is really in the pudding. What happens when we use superfine attributes to actually identify people? So this is the machine learning bit. I'm afraid it's very simple. We just trained a ResNet 152 model. We trained it as a binary classifier and as a superfine attribute regression. So for binary classification, we had the original binary gender and age labels and a few other attributes on there. So we just used binary cross entropy for that. It's pretty straightforward. Superfine regression, again, very straightforward. We just use a mean squared error loss function because it's a continuous space. And the results are pretty outstanding. So for just gender and age, just the gender and age attributes for superfine and binary, we see that superfine outperformed binary by 8.25% on the area under the curve. So it's a much better predictor for actually finding that person's unique identity just from an age and a gender annotation. What's even more outstanding is that when we have 3 superfine attributes and we compare that to 35 binary attributes, we see that superfine still outperforms by 4%. And that's because the labels are much more discriminative. They're also more objective, so the labels are much more relevant for those images. So the machine is able to learn a better representation for each image. So just a little bit of TensorFlow. It's very high level. It's not anything that's spectacularly mind-blowing. Just a few little patterns that we learned that were kind of useful on the way while I was doing the research and just helped iterate a lot faster the solutions we were drawing up. So I remember when I was learning TensorFlow, my mind was an absolute mess when it came to loading data in. It was a completely different way of doing it. I was used to the graph structure, but TensorFlow seemed to be smoking a joint or something when it came to loading data. So I happened across this pattern which worked really nicely. So it's using a sliced input producer, which sounds kind of complicated, but essentially it just takes a list of tensors, and those tensors are preloaded from CSV and just converted to tensors. And what the sliced input producer does, it just shuffles all those tensors together, and it gives you one element of each back. And then you can load in your images, you can do your pre-processing, and then the TF-train batch finishes off the producer and actually sends the rest of the graph, your batch that you actually want. And this is really flexible because it means you can add in another tensor if you want to have some metadata that's working alongside your training data, your validation, and there's not too much to fiddle with. It's not as efficient as, say, using a TF record, but it's a lot more flexible. The second one is going into this function here, read image path, so we're reading the image in. We want to do a lot of augmentation on the images because we want to increase the variance and improve the robustness of the model that we're actually learning. And there's a bunch of ways of doing this. Again, this is just a really simple way I just found was quite powerful and flexible. So we use the command line to set up the experiment. And we can actually just write into the argument there just a comma separated list of the pipelines that we want to use. So do we want to flip it? Do we want to sample the B-box or change the color or stretch the image? And then when we run it in Python and create the graph, we just split that string on comma, and we work out, we have a dictionary which is that string to the correct function which returns the graph for that augmentation stage, and we just pile them together and draw out the graph like that. It's super basic, but I just found this pattern really helped to more rapidly develop what we were doing. Okay, so we're in a pretty good stage right now. We've got a pretty cool demographic estimator, but sat down with Jamie and we want to take it to the next level. So at the moment we're just working with static images, so we wanted to really bring it to the real world and apply it to video. So this is the technology that we use behind Aura Vision, and this is actually from a very early prototype we built last year. As you can see, we're tracking and detecting every single person that walks down this high street, and on top of that, we're estimating their age and their gender and a few other clothing attributes. So you can see this lady actually gets her wrong, and then it updates her label to female because it gets more accurate and does more estimations as they walk through the scene. Can I take questions afterwards? I'll be all right. So don't have much time. So this is an experiment. So we worked in many different environments. This is actually something we ran early at our university. And this is the product that we give back to our clients. So this is our early stage dashboard. So this is really pulling out analytics from this scene. So this is what the machine sees, but this is what our clients see. And we're measuring footfall counts. We can break them down by gender, by age. We can do fairly complex queries. We can say who comes into the scene, who then waits in the chair, and break that down by demographic. We can tell where they entered and then where they left the scene, what they did in between, how long they spent in different areas, how people moved through the area, and then we can break that down and segment it by a specific demographic. So you could say 80% of people move from right to left, but actually your target demographic, females 16-24, 80% of them are moving right. So there's a massive amount of insights we can get out of this. The last bit of TensorFlow that I'm going to run through is that in order to solve that problem, we needed to train multiple different models on different data sets. This posed a bit of a challenge at the beginning, because we're like, well, how do you combine multiple models at production time together? But it turns out it's really easy with TensorFlow because of the way the graphs are structured, and you've got the variable scoping. So we simply initialize the network, and we have different variable scopes for different stages of the model. We then train those models separately in their own training harnesses on different data sets, doing their own thing. And then when we want to load in those checkpoints, we just create a saver, and we just say, I want all the variables in the graph that we've initialized, and I only want to select the ones that are, say, from model stage 1, and then restore that checkpoint into those. And we do that for each and every model that we want to load in. And that's actually what we do at production time to get all these different models to run in the same graph at the same time much more efficiently. So the last stage is, okay, we've got this cool tech, it runs in video, what do we do with it? We need to commercialize it. So we spent about 3 months talking to just everyone that we could. We actually went to CES in Las Vegas. I spoke to hundreds of people there, people from retail, shopping malls, advertising agencies, you name it, spoke to them. And it turned out that our technology really suited to help high street retailers answer a lot of the questions that they have. So we really narrowed our focus down to solving their problems. So the retail analytics space is super competitive. There are loads and loads of people counting solutions, loads of technologies out there. Some of them do some stuff better than us, but we do a lot of things better than them. For example, Wi-Fi tracking is really good at doing repeat visits, but it's not very precise. You can't accurately say someone's standing in front of your product. So there were some design decisions we had to make, and the very first one that we made when we incorporated the company was to be 100% anonymous. So we completely shifted away from security and identifying people. We actually used the demographics to protect people's anonymity. So GDPR was a topic that was becoming mainstream when we incorporated, and we felt this was really important to follow this through. 5 minutes left. Brilliant. And, so we don't store any personal data. Shoppers are never identified, and we see their demographics, but they're aggregated over time, so you can never individuate a person from our data and link it back to something else. On top of this, there's minimal installation, because we can integrate with existing CCTV cameras, because it can work anywhere, and it works in such a number of different environments. We can answer a lot of different questions. We can run it on the high street, in the entrance of the store, on the shop floor, looking at product aisles. It's extremely versatile. So the product that we actually offer back is really simple. So we integrate with existing CCTV cameras. So we have this little tiny PC. It's really low powered. Jamie spent the last 6 months slaving away on this thing. I think this is about to break into tears if I say anything bad about it. But it's really great because it just plugs into the CCTV system that's already there in the store. So the retailer doesn't need to go and set loads of cameras up. They don't need to put Bluetooth beacons in the ceiling or Wi-Fi beacons in the ceiling. You just plug this thing in, you switch it on, and it streams all the video to our cloud processing servers where we do all the heavy lifting. So in the cloud, we process the video, and the data that we put back is all entirely anonymous. The video gets thrown away, and what we're left with is this dashboard which our clients can log into, and they can see all of their reports and their insights from their stores. And the real uplift from this is that they can measure their store's performance like they can never measure it before. So for example, if they're running a marketing campaign, they spent £100,000 on this TV campaign to target females 25 to 34, they need to know, is that actually working in their stores? So before they have a footfall counter, say, yeah, a few more people came into your store, but did it actually work? Now we can actually tell them how many of that demographic that they were targeting came into their store. If they shift a shelving unit and they're trying to have people engage with their product more, we can actually measure that and tell them not only the people who are engaging more with it, the types of people that we're engaging and what they're doing in the store. So that's it. Thanks so much for listening. I look forward to answering your questions.
Right, I want to do the money.
Yeah.
So check the back. If you could just give your name and the organisation you represent.
Robin and IHS Market. And the first screen that you showed us was of a serious situation where you're trying to identify some criminals. Your system is actually working on people that aren't trying to trick the system. How easy is it to trick?
How easy is it to trick?
Yeah, so if I wore like a I don't know, success or something, would it be like, oh, obviously
It probably would, yeah. So, I mean, I come up as like a 95-year plus male because obviously my so there's not much you can do about that. I mean, it is down to the data that we've seen before, and essentially, yeah, the system is stereotyping. It is based on visual stereotypes of people. We find that that's pretty accurate on the whole, because when we validate it, we get multiple people to label those images, so we can tell how consistent are people with each other. And obviously how consistent is the machine with the crowd's consensus as well.
So it's not necessarily got space in the security space yet. It's not pointing towards the security space yet. It could be tricked, yes.
The underlying algorithms could be used. I mean, that's why they were developed, and they are used to do that. That's essentially how facial recognition, if you're estimating gender and age from that, it's going to work on a similar premise. But because we create the company to be entirely anonymous, we wouldn't take that into the security space.
I saw Gate was missing from one of the tags that you give to someone. The Gate is like a kind of quite difficult to fake now.
Yeah.
It's not there. Is it something that is there but I just didn't see it, or did you think about Gate?
Yeah, we've thought about Gate because so Jamie and myself, we had the same supervisor at the University of Southampton. He was actually the guy, Professor Mark Nixon, who's actually the guy that invented gait recognition. So, yeah, we know all about gait. And actually, the soft biometrics come out of a lot of the gait stuff because you can't often see the gait in CCTV images. If you've got multiple people standing in front of each other, you might be able to see a headshot, but you're not going to be able to see their legs moving. And that's actually part of the idea where soft biometrics came from.
Just it. No, just here on the left.
Hi, do you have a minimum threshold for your analytics data, i.e. minimum number of pixels to say, right, you can now classify this person as being this age, gender, and so on?
Yeah, sure. So we'll classify anything that we can detect in the image, but obviously there's a minimum size that we can detect. So with the camera angles, we wouldn't say point the camera off into the horizon, like most CCTV systems won't be set up to do that. They'll be pointing down a bit, and then you can ensure that people are large enough to actually detect and get decent estimations on them. If you point it off into the horizon, people just shrink rapidly and it becomes pretty tough, yeah.
Just here on the right. Your name?
Hi, it's Christopher, Sports Vision, and what I wanted to ask was, you showed the inputs to your convolutional neural network, and what I didn't see was the inputs. You said you have the superfine features, and is it superfine features plus the image? I imagine.
Yeah.
And is that you regress those separately, or?
So the superfine attributes are essentially just labels. They're your Y, and your images being your X. So all we're trying to do is get the model to estimate the Y from the X. So it's just like you would with binary or categorical attributes.
Oh, okay.
Yeah.
Okay, so you get those attributes. Then do you then further, or you simply just get those attributes rather than get a binary output instead?
Yeah, so you get a continuous output instead. So for example, for gender, if you're putting in the two axes, we put in, there will be two separate elements in the Y. We'll get two responses back, and then we'll interpret that as a gender classification. And if you want to categorize it, you can work out where it is in the space and actually cluster it to the right region, and you categorize it.
Okay.
Does that answer your question?
Yeah. I completely misread something.
Time for one more. Yeah, that's it.
Hi Daniel, my name's Robin as well, working in Smart Context. With retail applications, have you thought about the Amazon Go style where you can identify someone in flight, as long as they take themselves in store and then they can just walk out with a product?
Yeah, so Amazon Go is really interesting. Thanks for bringing that up. So what Amazon are doing are they want to create their stores from the ground up. So they brought out this grocery train in the US. So they really want to just restructure retail, and their solution is fantastic. But it uses a massive amount of hardware. I mean, hundreds of thousands of pounds worth of kit in that Seattle store. There's cameras lined across the ceilings everywhere. It's fantastic what they're able to do with that and the engineering feat of that. But we don't see that as a scalable solution right yet. There's quite a few other startups that focus on pose estimation, so tracking your limbs, seeing how you interact with products. They're really cool, and there's some really awesome open source algorithms like OpenPose that do that. But they need to have very precise, very precision cameras. They're very high quality. We don't see that as a scalable solution for the types of clients that we're working with, who are at the moment really underserved by everyone else in the market. That's why we're going down the CCTV route using existing cameras.
Thank you.
Thanks, Daniel.
Thank you so much. Cheers.